Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. It's my great pleasure to introduce today's speaker, Dr. Venkata Krishnan. Dr. Venkata Krishnan is an assistant professor of computer science at University of Illinois at Chicago. He is co-founder and co-director of the Center for Research and Instruction in Technologies for Electronic Security at UIC. And his main research areas include web application security, browser security, mobile code security, and data thinning mechanism for addressing information flow confidentiality. He received his PhD degree from Stony Brook University in 2004, and he is the recipient of the Best Research Paper Award at ACSEC 2003 and the UIC College of Engineering Teaching Award in 2007. And today, Venkat will talk about how to defend against SQL injection.
Thank you, Inkhui. It's a pleasure to be here, and today I'm going to talk about SQL injection attacks. And this is joint work with my student Prithvi Bisht, who is at UIC, and Shruti Bandakavi, who is a student at UIUC, and P. Madhusudan, who is a professor of computer science in UIUC. So let's start with a very simple example. What we are looking at is a phone book record manager, which allows users to edit their phone book entries. So this is the architecture of the whole setup. You have a web browser. The browser, receives this page, and that page is provided to the browser by a web application server. The web application server, when it gets some user input from the browser, it sends it to the database in the form of a SQL query, and the result is sent back to the application server, which then formats the result in a web page, and it's sent back to the browser. So this is a simple web application that will illustrate some of the ideas that we're going to talk about today. So consider the case where the user enters his name John and password Open Sesame. The phone book application allows users to either display or delete their phone book entries. So if the user chooses display, the phone book entries are displayed provided the username and password are right. And if the user chooses delete, the phone book entry is deleted if, again, the username and password are right. So let's say the user chooses display. In this case, the SQL query that's generated by the web application server looks like this. It is select star from phone book, where username is John and password is Open Sesame. And the result in this case is that John's phone book entries are displayed on the browser web page. Right? So let's look at, this is the typical scenario of the use of this web application. Let's look at an attack scenario. Okay? The user inputs John followed by a single quote or 1 = 1 followed by the 2 dashes. As you all know, the 2 dashes represent the comment character in SQL language. And let's say the user he enters a password that says the password is not needed and chooses display. Right? In this case, let's see what happens. The query generated looks like this. Select star from phone book, where username is John, or 1 = 1 followed by comment and a whole bunch of things. Okay, and password equals not needed. In this case, because the comment character appears here, the rest of the query is commented out, and the condition 1 = 1 is always true. So all the phone book entries are displayed because 1 = 1 is always true. So in this case, the attacker is able to access all the entries stored in the database by a simple attack. So SQL injection attacks are a major threat on the internet today. These are the data recorded from the Common Vulnerability Index, and in 2004, among all reported attacks, SQL injection contributed to 5.5%. And in 2006, if you look at the same data from CVE, it's grown threefold to 14%. In fact, in 2007, thank you. 2007 August, a report was released by Symantec where almost 63% of all vulnerabilities reported on the internet were either SQL injection or cross-site scripting. So SQL injection is a very significant threat, and last year in the card system security breach, about 263,000 customer credit card numbers were stolen and about 40 million were exposed. So this was covered widely in the media. So this is a very important problem. So in this talk, I'm going to talk about the following. We want to take a web application and we want to transform the web application and render it safe against all SQL injection attacks. And what I'm going to talk about is something extremely simple, and I believe it has certain novel characteristics. But the technique itself is very simple and very intuitive. And this appeared in ACMC CCS 2007. So let's look at SQL injection again and refer back to the example. So in the example, we saw that there was a lack of separation between code and data. That is, user input, input coming from the user that's untrusted is influencing the query. In the example, we had an R coming from the user, which allowed the query to be changed, right? So SQL queries can be constructed in a program by arbitrary sequence of programming constructs, and these involve string operations like concatenation, substring, and so on. And such constructs do involve untrusted user inputs. And normal cases, such input should be treated as mere data. If a user supplies an R, that should go as a username with maybe R or a password with R. But in this case, it's influencing the query. It's influencing the way the query is structured. And so the queries intended by the programmer can be changed by untrusted user inputs. And this is the problem in SQL injection. So we want to dwell on this notion of change a bit before we understand this problem further. So let's look at the parse structure for a benign query. So the query looks like this: select star from phone book where username is John and password is Open Sesame. So now this is the parse tree for the query. So there's a whole bunch of things on the left which parse select star from phone book, which are not very interesting. The most interesting thing in this picture is the where clause, where the where clause contains a condition term, the keyword where followed by a condition term. And the condition in this case is an AND condition, which has two subconditions: username equals John and password equals Open Sesame. Now consider the parse tree structure for an attack query. First of all, the query actually has a where clause. In addition, it has a comment. The query has, the left hand side is the same. It has a where clause and it has a comment. So, and then this, you have a condition term, but the condition term contains an OR. So what I'm trying to say here is that the query structure or the parse tree structure of a benign query is completely different from that of an attack query. So if you see here, you have an AND in the condition term, whereas an OR in the condition term in the attack query. And you have a comment, and you don't have a comment here. So if you have the token, the parse structure of the two trees, this is the programmer intended query, and this is benign query, and this is the attack query. So the parse trees are not isomorphic. So this is an observation that has been made in several works on SQL injection. So we want to start from here. So the best defense against SQL injection are what are known as prepared statements. So prepared statements exactly address the problem of separating code from data. So in MySQL, on the prompt, you can issue a query in the form of a prepared statement like this. So you can say prepare statement name from select star from phone book where username is question mark and password equals question mark. Now these question marks represent placeholders for input. So any user input will go in here, but it will never be used to parse the query. So the query is parsed even before user input is received. And so this provides a convenient mechanism to separate this query structure from any data that the program reads. Right? So the statements are parsed once without any user input and not for every user input, and this is the parse tree for this query. So it is the best defense because now you have ensured that user input will never influence the query structure. Right? So the problem is with legacy applications or applications that we use today, applications that are deployed today. Adding prepared statements to them will prevent all SQL injection attacks, but it's hard to do them automatically. We are talking about applications that are millions of lines of code, and for each application, for each query location, we need to guess the structure of the query. In order to write a statement like this, we need to know what the query structure looks like at each query issue point. And this is hard to do by static techniques because the query may depend on the particular path taken in the program, and it may involve several procedures, and static techniques usually make approximations, and so it's hard to do this by static techniques. So one other option is to have a programmer sit with the application, understand the application, and add these prepared statements and not allow the program to dynamically construct query strings. Now this is an option, but these changes are fairly non-trivial, and it is expensive to employ human efforts to do this kind of thing. So the natural question that we can ask then is whether it's possible to infer the query structure dynamically, and that's the problem that we address in this talk. So here is what we are said to do. So there is an application and it receives actual inputs. Now these inputs may be malicious, and what we want to do is to provide candidate or sample inputs to the application. So we provide candidate inputs to the application receives actual inputs. Now we want to execute the web application simultaneously over actual inputs and candidate inputs. Now the program on executing over actual inputs and candidate inputs will result in two queries. There is an actual query and there will be a candidate query. So the actual query is possibly malicious because it came with actual untrusted user input. The candidate query is always non-attacking by construction. So now you have an actual query and you have a candidate query. You can compare the structures of these two queries. If the structures match, then you send the query to the database. If the structures don't match, then you disallow the query from being executed. So this is what we are set to do, and so we have reduced the problem of SQL injection to the problem of guessing these candidate inputs, because if somebody gives me these candidate inputs, then I can do the whole thing, compare the query structures of the candidate query and the real query, and prevent any possible SQL injection attacks. So we have to find a bunch of candidate inputs that first of all are benign, and issue a query at the same query location. So look at this application to the right. It gives sort of the graph, the flow graph of a particular application. So you have actual inputs, and the actual inputs take the program to a particular query issue location. So let's say this yellow location is a program point which issues a query to the database. Right? So we want to find candidate inputs that will take the application through the same path and issue a query. So now if we are able to do that, then we can compare the query structures before the actual query is issued and detect SQL injection attacks. So, but in general, guessing these candidate inputs that will take you to the same query location is hard. It's in the most general case, it's undecidable. So it is a hard problem, and so what we want to do is to avoid this problem. So our idea is to first of all start with manifestly benign candidate inputs. So for every string, let's say user input is John, we want to create some manifestly benign inputs. So a simple manifestly benign input is a string of A's. So for every string, create a sample string of A's of the same length. So for John, I will create a string of 4 A's. So for password, if it is OS, I'll create a string of 2 A's, right? And let's say I assign Boolean variables always true. I assign integer variables always to the value 1, right? Now the candidate input to this program is, uname is 4 A's, password is 2 A's, and then display is true. So these, inputs by construction are benign, right? A string of A's will, definitely not result in a SQL injection attack, provided the program itself is, not constructing attacks, right? So we have solved the first problem. We have created benign candidate inputs. Now we want these inputs to issue a query at the same query issue location, right? So the actual program may take these candidate inputs and take the program. It may take the program along the same path to the query issue location. So let's look at this in more detail. So you have the original phone book application. You have input string username, string password, and the Boolean display, which when true you will issue a select query, which when false you will issue a delete query. So now look at the original input. It's John, password is OS, and display is true. So we create candidate inputs that are a string of 4 A's, password is AA, and display is true. So now if I issue these, if I run the program simultaneously over these two inputs, I'm going to get two queries. Look at the actual query. Select star from phone book where username is John and password is OS. Right? And the candidate query is select star from phone book where username is 4 A's and password is A. The query structures are the same. Right? So username is same, and both queries have an AND clause. The only thing that differs is the actual literal string used in user input. So that's fine. So now let's look at another case where the user chooses John, password OS, and display to be false. He wants to delete, right? So now let's say I according to my earlier set of premises, I start with username A and password A and display true. So the original program will proceed along this path because display is false. Now my candidate query will proceed along this path and it will give me a select query instead of a delete query. This is a problem, right? I mean, now if I compare, even though the inputs are benign, I'm going to get two different queries. The query structures don't match, but it's not the case that the program is under attack. So because the candidate query does not take the program along the same control path. So look at the actual queries. The actual query is delete star from phone book. The candidate query is select star from phone book. There itself there is no match, right? Even though the actual inputs are benign. So what we've learned here is that the query structure depends on the control path that's taken. So if the program takes this control path, then this is for this query location, and for this path there is a particular query structure. And if the program takes another path, say this path, then there is a different query structure. So it depends on the control path taken by the actual input. So what we want to do is to reject this candidate path. Instead, take the candidate inputs and force it along the same control path the actual inputs took the program to. So what this means is that when the program has a condition, I don't evaluate the condition on both candidate inputs and actual inputs. I evaluate it only on actual inputs and let that take the program to the particular query location. And at that point, I will compute the candidate query and I'll check the candidate query versus the actual query. So what this means is that I won't take this candidate input. I won't consider Boolean variables in my candidate input. So I will just take candidate inputs of a string of A's and password is AA. And if the original program takes this path, the candidate input will also take this path, because now I'm evaluating display, the condition on display, only on the actual input. So display is true, display is false according to the actual input. So that will drive the program to the actual location. So now, I'm sorry, the query should match. There is a mistake in these slides. So evaluating queries on actual inputs results in the same delete query for the candidate query as well as the actual query. So this is the trick we employ. So the formalism behind this approach is fairly intuitive and simple. So when you construct a query can be viewed as a symbolic expression on the actual path that is being taken by the application. So you have an application, there are conditionals, and in the body of the conditionals there are string concatenation operations. If you collect them and put them together, you get a large symbolic expression that actually represents the query. So when you substitute the actual inputs, you get the actual query. When you substitute benign inputs, you get the candidate query. If these structures match, then it's not a SQL injection attack, and if these structures match, then if it doesn't match, then it's an attack, and if it matches, then it's not an attack. So the benign candidate query is obtained by replacing the symbolic inputs with benign inputs, right? So this is how my transformation looks. So for every string in the program, I add candidate variable. So you have a string uname, that's an input, and you have a string password, that's an input. So you add a candidate string. So this is a direct source transformation. So you add the variable uname underscore c, and you add the variable password underscore c. So now I look at every operation done by the program, and I sort of shadow the operation on the candidate input. So in this case, uname, first of all, I initialize the samples. So uname is initialized to a sample. So if input 1 is John, then sample is a string of 4 A's. If input 2 is password, that is OS, then password candidate variable for the password is a string of 2 A's. Right? So now look at how I transform. So I don't transform the condition. The condition is on the real variable. So now let's look at the body of the condition. You have the query, the delete query being computed. So we already added a candidate variable query underscore c. So we just shadow the operation, except that we replace the original variables by the candidate variable. So the original query had uname, so I replace that with uname underscore c, password with password underscore c. In a similar way, I do that for the select query too. So I just shadow the whole operation, replace the original variables by candidate variables. So now when I come to execute query, I transform that statement into a statement that tries to match the query structures of query and query underscore c. If these two match, then I execute the query. If not, I just deny execution of the query. So we've seen the basic idea behind CANDID, and now I want to give a couple of examples that show that the technique is remarkably resilient in several practical situations. So let's look at input splitting function. So what it does, this application, it takes a string like Alan Turing, and it results in a query where it splits the name into first name and last name. So it results in a query where you say select star from table where first name equals Alan and last name equals Turing. Right? So now our candidate input for Alan Turing is going to be a string of maybe 11 A's, right? So the place where the space appears is index 4, right? So now the function actually takes the first 4 characters and the last 6 characters. So let's see what the candidate transformation does. It starts with a candidate input of all A's, because it doesn't know the logic of the application. It just initializes the input with a string of all A's of equal length. Now the instrumented input splitting function, what it does, it gets the value of space index because we don't transform integers. So fn underscore c is input of input c from 0 to 3, which is a string of all A's, and ln underscore c, the last name candidate variable, is a string of 6 A's. Right? So corresponding to Alan and corresponding to Turing. So the query generated will be select from table where first name equals string of 4 A's and last names. So if you compare the two query structures, they are the same. So in a typical input splitting application, the transformation works. Surprisingly simple transformation works. So let's look at another situation where the query depends on some predicted over input. So let's say the input is John, Jane, Mary, and what the application does is counts the number of words in the application and constructs a query based on the number of words in the application. So like a natural language search, for instance. So now the query is I'm only showing the where clause here, where name equals John, name equals Jane, or name equals Mary. Right? So let's look at what CANDID does. So so CANDID initializes this with a string of all A's and results in a query with exactly 3 clauses, name equals something, name equals something, and name equals something. So you have the exact number of clauses matching based on the logic of the application. So if you have 2 words, John and Jane, it will still result in a query with just 2 clauses. So it's kind of neat and resilient for these situations. So if the input is just John and Jane, then you result in a query with just 2 clauses. Okay, so this is how the implementation works. There's an original program, and then we do the CANDID transformation on Java bytecodes. Bytecode transformation is particularly advantageous because you don't require access to source code of the applications, and this is all done offline. So what you have is an instrumented web application that does this CANDID transformation. Now online, when the browser makes a request to the instrumented web application, whenever the program issues a query, we refer to a SQL parse tree checker that compares the real and candidate queries. If these match, then the query is allowed to go to the database. So we evaluated CANDID over a suite of 7 applications, and 5 of these are commercial open source applications obtained from gotocode.com, and we used it against an attack suite that had 30 different attack patterns. So these attack patterns were constructed from common SQL injection patterns that were available from certain CC advisories, and these attacks were constructed by an independent research group. And the test suite also contains benign inputs that are used to test for any kind of false alarms that CANDID may generate. And this is how we did the testing. So we ran the system, the instrumented application, on a virtual machine. We ran the original application on another virtual machine, and we ran a tester application that issued these web queries simultaneously to the original application and the instrumented application, and it classified them as attack, benign, or parse errors. And these are the results from our experiments. So as you see, first of all, these applications are fairly large, over 10-15,000 lines of code. We believe the CANDID approach can scale to applications that are considerably larger in size because it's extremely simple. And we had a number of attacks for each application, in which in every case CANDID detected all the attacks. And we also had non-attack benign strings that contained SQL injection like patterns, but which were actually benign, and those did not raise any false alarms. And there were a few queries that did not parse correctly and that were directly rejected by the backend MySQL parser, and we classified them separately. So this is the performance numbers. We have all the applications listed here. So the blue one represents the original application time, response time in milliseconds. So what we did was provide a query to the web application and measure the response time. And the yellow one is the transformed application with the parse tree comparison. And the green is the transformed application but without the call to the parse trees. So as you see, the transformation itself has negligible overheads, and the parse tree encounters a small amount of overhead. In most cases it's about 20%. So we believe that CANDID can be implemented very efficiently, and if we used a more efficient hand coded parser for SQL, we used a very generic parser generator based SQL parser, and so there was a bit of overhead there, but we believe it can be implemented very efficiently. So after the original paper describes CANDID implementation at the bytecode level, but since the transformation was extremely simple, we could we implemented CANDID both at the source and JVM levels. Each of these levels have their own advantages, and for instance what we did with the JVM was to have a candidate string for every string in the program, not just user inputs. Now the advantage of that is that you can run your web application over this instrumented VM and not do any changes to the original application. So all you do is to change your Java interpreter to this new JVM that does candidate tracking, and then you get safe web application that runs on top of it. So this is particularly advantageous, but since we are doing candidate tracking for almost all string variables in the program, there is a considerable overhead for that, and it can be minimized by propagating candidate strings which depend on user input, and that's what we are currently doing. So there is some more recent work, basically mostly related to dynamic techniques and static techniques for prevention of SQL injection attacks. First of all, the most common defense employed is input validation, but it is kind of well known that these are not robust against different formats of strings. So for instance, if the backend uses alternate encodings, the attacker will be able to inject SQL commands into user inputs that make use of these encodings, and this may slip through the input validation function. And mostly, programmers, there are lots of bulletin board forums which describe how these input validation routines can go wrong. So the notion of comparing parse trees is a much more robust notion for defending SQL injection attacks. So there are static analysis techniques that that solve a slightly different problem. They are used for merely identifying which user inputs reach a SQL query without being validated. So that's the objective of static analysis techniques. So they are merely used to identify vulnerable applications, vulnerable locations in an application. They do not offer, so for instance, if an application does input validation, they do not offer any assistance to check the soundness of the sanitizing routines. And another recent work involves use of static analysis to build query structures and use that for dynamically preventing attacks. So you can guess the structure using static analysis at each query issue location, and then at runtime you can see whether the query received matches any of the queries that you learned by static analysis. And we've shown in the paper that this is not robust when the query depends on predicates over the input, because it loses track of control flow. So there are other dynamic techniques that people have worked on. So primarily it involves information flow tainting. So you taint user inputs as it enters the program, and then you see whether the tainted input contributes to SQL query structure. And these we believe are the best defenses for SQL injection. We also have a very detailed comparison. So for instance, when you have a third-party function for which you don't have access to, using a tainting mechanism, you should assume that, for instance, all the result that comes back from the third-party function is all tainted, and so this may generate false positives. But using CANDID, if the function doesn't have side effects, you can make calls to the function twice. You just apply the candidate string once and the actual string once, and then you get back the results and compute the candidate query. So there are several detailed comparisons that are shown in our paper. And so the contributions of this talk are primarily a technique to defend SQL injection attacks by guessing or deducing the programmer intended query structures at runtime. And it's resilient to different scenarios that might occur in real code. And we did several experiments on real code, and all attacks were defended, and there were 0 false positives. And and the message that we want to give at the end of this talk is that dynamic techniques are best suited for defending SQL injection attacks.
Time for a question?
I'm early. We got a lot of time.
So, your approach works for Java. So, if you want to use your approach for other programs,
It shouldn't matter. The language shouldn't matter at all, because the transformation is extremely simple as long as you can implement this. So the JVM approach works for applications written in Java, JSP, and so on. But if the transformation itself is not complicated. It's just replicating or shadowing the operations done on real variables. You can even use some kind of textual parser to implement the transformation. That's probably what's needed, nothing more, because all it requires is initializing the candidate variables and then replicating the operations done on real variables and candidate variables. So it should be fairly easy to implement on any programming language, provided you want to do the source transformation. So does it address your question?
So could you go to the slide where you have 3 usernames and then separated by space? Mm-hmm. So I think the effectiveness depends on the string operation. So suppose I have a function which returns the substring ended at the first space. And then I issue that call, and then I get the first substring. And then the second call is I get the next portion that are from the first space and the second space. Mm-hmm. So then if the string is here, then the first call will get John, the second call will get Jane, and the third will get Mary. But if I issue it on this input, the first will be all A, the second will be empty string.
So it depends on where you implement the transfer. So are you doing the call to that function? So are you looking at where the space is in the code, and then you are making a call to return?
So if the function get an integer index and then get a substring, so this would work. Mm-hmm. But if the function, the library call directly return a substring, start from the beginning, ending at the first space. So because it's a string operation, I guess you would issue the same call on the string method and then.
But as I see it, the logic of the original application is now put in this third-party library function. Is that what you're saying? So now the library function will have to do the same thing. It has to search for the string based on, it has an integer value, and then it computes a substring. Right?
So this is really, for example, in Java, they probably, I don't remember the string API, they probably do not have this function. So you're going to kind of change the Java library function source as well if it's implemented?
So we are doing it at the bytecode level. So for instance, we can transform everything that is available in bytecode form.
So then it will work at the JVM level, but if you do source transformation, then that may not work. Right?
So in that we are assuming here that the source for that library function is also available if you're doing that.
So you're also.
But our primary implementation is on bytecode, so it will work on everything. Okay. So it depends on how deep you can go into the implementation of the functions. Mm-hmm. So at some level, if there is a call, and if the call has if the source for that is not available, then yeah. But then you can do this bytecode transformation and.
But then for other languages
So all library functions in Java have this property that the length of the string, so we have this notion of length preserving the paper. Mm-hmm. So almost all functions in Java are length preserving, which means that all our transformation is sound for all the functions in Java API. But I'm sure you can create a situation using a third party function, right, which has a side effect. Side effect as in this case, it depends on some value which is not available to CANDID, in which case the real and the candidate strings may differ. Right? But we have not encountered such a function in the actual examples that we have tested, and we believe that if given access to all the sources, our transformation will work. Yes.
I could be wrong, but I think in Java strings are constant. When you create a string, you can't change it without changing the arguments.
No, but so I don't.
So you would worry about the length changing the string because.
No, but it's not just a string. I mean, you compute a string from another string. So you take a string and do a substring, and you compute another string. So you need to create a candidate string for this new string that's being constructed, and so even though strings are not manipulated directly, you can do string operations and get new strings as a result of those operations. So in which case you have to create these candidate strings.